Greetings. We have seen that if we have a function, f of x, we can create a new function called the derivative, f prime of x. But we have to be careful because the derivative will not always be defined for each value in the domain of the original function. Let's actually take a look at this. A function f is called differentiable at a if f prime of a exists, meaning if the derivative exists at that point. And then we can say it is differentiable on an open interval from a to b, or from a to infinity, or negative infinity to a, or negative infinity to positive infinity, if it is differentiable at every number on that interval. I know this might seem like a lot to take in, but basically we're saying sometimes the derivative, which we know is defined to be that limit of the difference of function values all over h as h goes to 0, that limit might not always exist. There are specific situations where it doesn't. And so we say that a function is differentiable when that limit does exist, and there might be points where a function is not differentiable. And I want to take a look at a few of these examples now to show you the situations where a function won't be differentiable. All right, let's take a look at an example. Specifically, I want to look at the function f of x equals the absolute value of x. And I want to talk about where this function is differentiable and where this function is not differentiable. Now, we have seen the graph of this function before. I'm going to draw just a very, very crude version of this graph. We know that it is a V shape. All right. So remember that the derivative is going to be the slope of the tangent line. And if we look at this function for positive values of x or for negative values of x, it is a linear function on those domains if we just look at the positives or we just look at the negatives. And we know that linear functions are differentiable. We've seen that before. We know that the derivative is just the slope of the line. So those points we don't have any problems. But if we were to look at x equals 0, we've got a corner there, which is a little harder to think about when we're thinking about the slope of a tangent line. So we might suspect that it's not differentiable there, but we don't want to just suspect. We want to actually think about it and have an idea. So what I want to do is I want to look at the limit there, but I want to focus on the right-handed limit and the left-handed limit at x equals 0. So let's look at that left-handed limit, the limit as h approaches 0 from the left of our function f of x plus h, but we're specifically looking at the point x equals 0. So this is going to be 0 plus h, the absolute value of, minus the absolute value of 0, all over h. Now, we know that the absolute value of 0 is just 0. So that second part of the numerator is going to vanish. And then in the first part, 0 plus h is just h. So we have the absolute value of h over h. All right, now remember, we're looking at the left-handed limit here. We're looking as h approaches 0 from the left. And so that means that for any value we're looking at here, h is going to be negative. And we know that when we take the absolute value of a negative, it becomes positive. We take the opposite of that negative value to get the positive value. And so really what we need to do is we need to replace this with the opposite of h. I know that might not seem intuitive, because when we take the absolute value of something, we know the result is positive. But remember that all of these values we're looking at have h as a negative number. So to make it positive, we have to take the opposite to turn that into a positive value. Now, once we've done that, and that only works for negative numbers in this situation, which is fine because we're just looking at numbers to the left of 0. Once we've done that, we can actually simplify this. Negative h over h is 1. So we've got the limit as h approaches 0 from the negative side of -1. And of course, that is just going to be -1 because the limit of a constant is just going to be that constant. So if we were to think of like the left-handed derivative, not that that's really a thing, but if we look at the left-handed limit portion of trying to find that derivative, we end up with -1. Now we can do the same thing for the right-handed limit, and we know that the limit is only going to exist if the left and right-handed limits both exist and are equal to each other. So we're going to have the same thing here when we're looking at the right-handed limit. Nothing changes in the beginning. I'm just plugging in our actual function. This is not 10. This is the absolute value of 0 plus h. And again, the next step ends up being the same because we're just remembering that the absolute value of 0 is 0 and 0 plus h is h. So again, we have the limit of the absolute value of h over h. But in this situation, we are looking at h approaching 0 from the right, so we're only looking at positive values of h. And when we have the absolute value of a positive number, it is just going to be that number itself. So here, we're going to have the limit as h approaches 0 from the right of h over h, which is just the limit as h approaches 0 from the right of 1. And the limit of a constant is that constant, so we get 1. So because the left and right-handed limits are not equal to each other, that tells us that the overall limit doesn't exist, and that means that this function is not differentiable at 0. So this is not differentiable at 0. So we have our first example of a situation where a function is not differentiable at a point. And the reason, if we look at this graph, that it's not differentiable here is because we have a sharp corner at that point. So if we're looking for places where a function is not going to be differentiable, one of those places is going to be if we have a sharp corner. It doesn't have to be a 90-degree corner like we saw here. It could be any other corner. But if we have a corner in the graph like that, then our function is not going to be differentiable there. There are a couple of other situations where a function is not going to be differentiable. I'm going to give you rough sketches of those. One of these situations is if we have a discontinuity, meaning that our function, our graph, is some sort of a nice curve, and then it jumps somewhere else, like that. So a discontinuity. In that situation, the derivative is not going to exist. The function will not be differentiable at that point because the left and right-handed limits are not going to be the same. And then the third place where we have a function is not differentiable is if we have a vertical tangent line. And I'm going to draw the tangent line in a different color here. If we have a vertical tangent line, and we get a vertical tangent line for the function f of x equals the cube root of x. This is a really good example where we have a vertical tangent line. These three situations are going to be situations where a function is not differentiable. And the reason this one is not going to be differentiable is because if the tangent line is vertical, that means the slope of it is undefined. And so the derivative is going to end up being undefined. It's going to be a limit that is undefined. So these are the three situations we need to be aware of where a function is not going to be differentiable.